Just a reminder, you do have until 6:45 to finish the quiz. That's 15 minutes from now. Just about 10 minutes remaining. Four minutes remaining. All right, time to hit submit. All right. So now that that stress is over with, everybody ready to move on? I got 1 thumb, 2, 3, 4. All right. So we're going to go back kind of towards the beginning of things. Just some trends that I was noticing, some things that I saw, like on the homework problems. For example, homework number 2 was when we were doing pacing. We were doing linear distances. Question number 1 gave us a surveyor who had gone out, paced out a known distance. So for 600 feet, he walked it 6 times, came up with those various that count of paces. Then he went and paced out an unknown distance from point A to point B and counted out 4 different times, 211, 212, 210, and 212. So the question asked us, what was the pace length and what was the length of AB? Just about everybody got this right. So it wasn't a matter of the calculations. It was more a matter of the reporting that I wanted to kind of address at this point. So to find the average number of paces over 600 feet, we find the average number of paces total, then divide the 600 feet by the 206 and come up with an average length, average number of feet per step, per pace. We carried that out to 2.91. What I wanted to address was the rounding that was happening. We were rounding, some people rounded a little too early in the problem. So when we took that to the next step, the second question, where we were looking for what's the length of AB. So again, we would take the average number of paces, multiply it by the number of paces per foot, or the number of feet per pace, and come out with 614.3 feet, which is great. But if we round a little too early, if we said, okay, well, the average length of the pace is 3 feet, we're selling ourselves short. We're coming up a little bit below what we should be, right? Actually, we're extending, we're overstating. So if we used 3 feet, then our length from A to B is 633.75 feet. If we round that again, we're at 634 feet. It gives us a difference of nearly 20 feet in error, okay? So 2 ways to look at that. What are the problems if we end up 20 feet off? We could end up on the neighbor's property if we're pacing something out. What do you guys think? What else could happen?
You charge by the foot. Yep.
Absolutely.
Right, Kenny. Yep. You could also be, well, I'm thinking construction terms, like fined for wherever you put an object as well.
Yeah.
Yeah. So.
Yeah. So what if that's exactly correct. So Kenny, Othello, great job. What if we end up, or we're paid by the foot? If we go out, and that's great because we're going to get overpaid unless it is a contract, a state contract, a civil contract, a public works contract with the city, with the county, with the state, with the federal government. If we turn in a record that says, oh no, it was 634 feet, when really it was 614, it doesn't matter if that 20 feet we get paid at a penny per foot or $100,000 per foot. We are in criminal miscompliance. We're in a criminal zone at that point. Okay. So that's one problem. That's the whole legality side of it. What if we're paying somebody by the foot to do this? So watch the rounding. Okay, just be careful when you're rounding. Carry out as many digits as is feasible while you're going through the problems until you get to the very end and circle your answer. Put it or box in your answer. Okay. Speaking of which, boxing in your answers. Only box in your answer. As you're going through, if you come up with an interim solution, an interim number that you're going to use later on, you don't need to box that in. It just makes it a little more confusing when I'm trying to grade those. So I want to be able to see all the work that you've gone through and just highlight the answer that you're turning in for me. Okay, makes it a little easier to track that down. All right, homework number 3, question number 4. And this was something that's kind of come along the whole stretch of the way. When you're given slopes as a percentage, this has tripped up just about everybody at some point. That percentage of slope is not an angular measurement. All it is a relative ratio saying that we have, for every 100 feet we go horizontally, we go whatever that percentage is vertically, okay? So in this example, we had 150 feet on our slope measurement, and it was a 15% slope. So that's our drawing. That's what we're trying to find out. We need our horizontal, we need our vertical. So the way to go about finding that, a lot of people took that 15% and took the tangent of it, took the cosine and the sine, and wound up figuring out the problem. But the answers were wrong. So slope as a percent tells us that for every 100 units, feet, meters, centimeters, doesn't matter. For 100 units of measure horizontally, we go X units vertically, okay? So that's something to watch out for when you see that percentage. So in order to solve this, what we're looking at is this horizontal 115 vertical. We can take the tangent of that. The tangent is that ratio, and find that angle. Then we can use the sine and cosine and our slope measurement to find our horizontal and our vertical. Okay. Does that help anybody clear things up a little bit more?
Yeah, it does, because I took the same approach, and it was, so I did the tangent. I don't think I used the sine and cosine afterwards, because I thought that the tangent would just be sufficient for some reason. So that helps. And sorry, I have to move my dog again.
That's fine. That's fine. All right. So homework number 3, question 4. So this kind of tripped everybody up too. It was just, I think the way the question was worded versus the reading, what we talked about in class, and then the way the question came across, it might have been unclear as to what we were looking for in terms of an answer on that. What were we expecting to see? So prepare a set of level notes for the data listed, perform a check. Everybody nailed that one. Elevation of benchmark 7 is given. Calculate and the surveying error and compare it with allowable. So boing, 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 boing. We've got our table. So that everybody pretty much has, right? Between the different labs, between the homework problems that made you do this over and over and over again, we're really good at these tables now. Finding the height of the instrument, finding the elevation, and moving our way through the course. To figure out the error, what we do is we sum up the back sites and we sum up the fore sites. To make sure we don't have a math error, then we also take the difference in elevation, our initial elevation, and our final calculated elevation, just to make sure we didn't transpose something, write down a number incorrectly. We want to make sure that those two are equal. Then our table jives, it balances. Okay. So here we've taken the difference between the back sites and the fore sites, and we've come up with an error of our measurements of 0.02. How do we know if that's good or not? How do we know if that's acceptable? Do we have to go out and do this again? So that's what we're looking for, is what is allowable? What's permissible? How close can we be and say, good, thank God I get to go home for the day, right? And how much do we say, well, somebody better get some floodlights out here because we're going to keep going. So what we're looking for here is this formula, that the allowable closure is based on the number of setups. So there's certain hiccups that we're going to encounter along the way. You know, the rod slips a little bit, maybe the tripod, one leg was on a little bit of a softer spot. There's going to be little flubs that happen along the way. We want to try and minimize those as much as possible. But when we do go out and start on our path, it's based on the number of setups, because we're saying there's an inherent error that comes with just setting up the equipment and doing the problem, and doing the process, right? So with each setup, we're saying that there is a little bit of an error, and we're willing to take a portion of that and agree that that's going to be as accurate as we can get. There's only so much we can do when we're reading those Philadelphia rods, okay? We do our best, there's still going to be those hiccups. So what the allowable closure on this is going to be, plus or minus 1/100th times the square root of 5, because there were 5 setups going through this course. First one, we went back and we set it up in the middle between benchmark 7 and our turning point 1. Then we just kind of leapfrogged ahead. In order to get back to benchmark 7, we had to set up our tripod and our system 5 times. So that's what we're looking for there. So that means that our allowable closure error is 0.022. So that's what the standards say our adjustment range is. So are we good? Can we go home, or do we stay there, call the rental yard and get some spotlight? What are we going to do? Okay. Kenny's giving us a thumbs up. I think he's just done. He's ready to go. Anybody else?
I think that does make sense for me, at least. I think the thing that I keep forgetting the most, and it's so simple, it's the plus or minus. And I just need to keep in mind that that's there. So.
Yeah. Yeah, we have to be within that range. We have to be under 22 thousandths either way. So yes, on this one, we do have our allowable is greater than our actual error. Therefore, we're good to go. Okay. Meet at the bar afterwards. Drop off the company truck. All right. This one hit us hard. So homework number 4, question 17. Everybody got pretty much all of this right. So what we were trying to find was, and that should have also come in at the same time, given the data here, we didn't have line 1, 2, or 2, 3, or 4, 1. We had one bearing for line 3, 4, and we had the interior angles for the other points. Okay, so everyone pretty much got 1 and 2 and 2 and 3 correct. So I'm just going to give those as a given. What seemed to bite everybody was figuring out from 4 back to 1. I couldn't find a common theme as to what was throwing everybody off. They were all just a little bit different. Okay, so what I did was I sketched it out. When in doubt, sketch it out. So I drew my line from point 3 to point 4. Okay. And we know what this angle is because we're given that as the bearing. I just converted it straight to a decimal so that the math is easier for me. I drew in my line from 4 to 1. And just so that I had the angles for reference, I drew my 0.1 to 0.2. So I can see what I'm looking at. I've just got that one little section here blown up a little bit bigger. We also know that our interior angle at 4 is 221 degrees. That was also a given. So what we're looking for here is our interior angle, our green angle here. So how do you want to go about solving that? Which math do you want to do? I'm going to record Othello's dog snoring and play that in the background instead of crickets. Add red and yellow and subtract 180. Yes. Olga, what were you saying?
Same thing. Never mind. I was too late to join.
Perfect. Yes. That's one way. Another way is 180 minus 78.9 minus 1.3 to give me my green angle. They're both going to be equal. Does that clear it up for anybody? Does that help?
Yeah, it does, because I did the yellow and red thing, and so that's a little more complicated, so it took me a little more time to set up the picture, and I may have had to do the picture a couple of times, but seeing it drawn out like this with the green angle made it easier to visualize. So
yeah. Well, and like I said last week, Kenny asked, are we okay? You know, can we turn in colors? Can we put colors on our drawings? Absolutely, as long as it doesn't look like a unicorn threw up on them. Make sure that they're meaningful, that they coordinate. Make sure it tells the story, not distract from it, okay? All right. This one. Question 2 on homework 5, so the one you just turned in. Find linear misclosure and check with third order class 1 allowable. We're going to assume that we've got 1 through 3 done, right? And that was to sketch it out to scale. I didn't set you up for that one, so that's going to be a give me. What were 2 and 3? Anybody remember? We needed to find the coordinates. And we needed to find the bearings. Oh, the bearings. Interior angles, right. All right, so we've done that. We're going to say we've done that. Now we need to find, just like we did on the traverse problem, or not the traverse problem, but the leveling problem. We need to find that error of closure and what value is allowable. We need to find the area of the traverse. It's a weird rhomboid kind of quadrilateral. Can't even say it's a square or a rectangle. It's a quadrilateral. We need to find the latitude and departure for each line. Remember, that's measured off a north-south meridian. And then we need to balance the latitude and the departure. So if we have an error in our closure, we need to spread that back amongst all of our readings to say, okay, proportionately, this is really where we are, okay? So assuming 1 and 3 are done, order and class for accuracy. The book does not cover this well. I have not covered it well, but there are federal standards for how accurate you need to be when you're talking a horizontal survey. Okay. You can see it goes from 16/1000ths of a foot accuracy up to plus or minus 33 feet. Where would we use each of those? Where do those come into play? So as you can see, I've got some examples down below here. The order is the first magnitude. The class then divides that into finer details, finer levels, okay? So first order, that's gotta be, pardon my language, gnat's ass. That is the utmost detail, that is the finite, things like benchmarks, where we're constantly going to be going back to it, we're constantly going to be referring to it, has to be dead on, okay? Those are going to be your first order types of accuracy and precision. Second order, things like bridges and tunnels. Not much leeway in terms of, if I'm putting a bridge here, I need to hit that mark. I need to be right on the nose. But they're a big enough structure that there's going to be a little bit more flexibility, a little more leeway in how precise our calculations are going to be. Construction surveys. Now, what's interesting here is that construction surveys are typically second order. That's going to be when the surveyor goes out and marks it. It's going to be a licensed professional. Construction staking is a third order level of accuracy. And what that does, what we're talking about there is when a contractor is out in the field, we're given specific points by our land surveyor, by a licensed professional. But from there, we don't get every single point on the map. It would take way too long and cost way too much money to go out and put every single specialty point that we might need in order to build a job. So construction staking, we reference a lot of what the surveyor gives us and branch off of that. So from there, once you take that level of precision of a second order construction survey and go off of that using the tools that we've seen so far, your accuracy drops a little bit more. So there's a lot more leeway when it comes to the construction staking side. Okay. All right. So what is acceptable for the work that we're going to be doing? Third order class 1 is, let's just use feet. 1 foot plus or minus for every 10,000 feet measured. That's still pretty detailed. So we have our coordinates. How do we figure out what numbers we're looking for? What was our error? What's our accurate, and what's our acceptable, or what's our allowable, sorry, not allowance. So our coordinates, from the previous section of the problem, we figured out what our coordinates were. So we backtrack from point D back to A to figure out, did we get the same number? It's just like we did with our back sights and our foresights. And then we took the difference between our initial elevation and our final elevation. That's what we're doing here. Only we're talking linear and angular measurements, or horizontal and angular measurements. So we know that line DA is 550.94 feet. And that angle here is 21 degrees, 17 minutes. So we calculate a delta X and a delta Y to get back to point A. And what we end up coming up with is a delta X of 513.37, a delta Y of 199.98. But if we look at what our coordinates at D are, if we were to take the opposite of those that's supposed to take us back to 0, 0, we're off a little bit. Half a foot here, almost half a foot the other way, okay? So what these numbers tell us, the signs do matter, okay? What this is telling us is that we are too far north and we are too far west in terms of our error of closure. Well, what is that distance? So if we calculate that distance, we find out that we are 67/100ths of a foot. Okay. What's the formula for precision? It's the amount of error over the total distance, right? The total measured amount. We saw that our acceptable is 1 in 10,000, but when we calculated out our precision, we're off by 67/100ths of a foot, but our perimeter's only 2,200 feet. Not very long. That's kind of a lot to be off. So when we round that out and go back to a 1 value, we say it's about 300 or 3,300 feet. Othello, question?
Yeah, so I did that. I found out it was unacceptable. But I also read in the textbook, if it's unacceptable, then you don't go through with the other problems. So that happens on the field. I know we did that for the homework, but you'd go back and
Yeah. Yeah, we'd have to figure out what happened here, because why keep going if we know we're wrong? If
right.
we are outside our tolerances, why would we keep going?
Okay.
Well, here it's to practice the math.
Yeah. And I also have another question. So instead of sine, I decided to use cosine since I heard from Kyle and I've been doing a little bit of more work myself. It's more, I guess, reliable, you could say.
Mhm.
So, and I got the same answer, but would you say that works as well for the most part?
Now, how are you using?
Cosine to do this to get to
Mhm.
this point. I just I decided that the departure and latitude were making right angles, and so I took
Mhm.
90 degrees and then that, and then took it from the other angle, and so and added in and then subtracted by 180. I'll go check through my work if you want. I can hop by office hours and we can talk about it. But
Yeah, yeah, let's do that, because I'm trying to make sure. It's like I said before, always and never are two very definitive words, and so I'm hesitant to say it's always going to work. I'm not going to contradict Kyle. Guy knows way more than I do, but I'd like to see how that's put into practice. Kyle, you
right,
got something?
Oh, cosine just always gives you a positive. So as long as you define your directionality correctly, cosine, you don't have to worry as much about any calculator errors. So I think it kind of gets to what Sarah's saying is that
Okay.
In this case, mathematically, it always gives you a positive because it's defined in your calculator as a positive. But it's like anything. Be careful and do a sanity check to make sure you're going the right direction. But I'm a cosine fan.
right, yeah. Well, and I saw it worked a little bit. Well, we'll talk about it later, but yeah, I just wanted to bring that up because that was kind of interesting with this whole thing as well.
Okay, yeah, let's go over it, and we can discuss it and present it to everybody else next week. Cool. All right, so we've got the distance from our original point to where we've calculated what our point is going to be. Over the course of the traverse, we find out what our allowable error is. It's unacceptable. Do it over. Okay. All right. So that takes us to step 2.5, finding the area of the traverse. Using the coordinate method. All right, there's two methods that are presented. The double meridian distance is a little harder to wrap your head around. The coordinate method makes a lot of sense to me, mostly because of how it's laid out and how it's presented in the book. The coordinate method is really set them up as a ratio. So your X coordinates on top, your Y coordinates on bottom, set them up as a line, and then it's from down and to the left and go across that way, and then up and to the right and go across that way. The nice thing is when you start with a point like 0, 0, that negates a lot of the math, right? So that gets rid of the first and the last on each side of it. Then taking the difference. So the book does go through and explains how it comes up with what this formula is, how we get there. Really what we're doing is we're taking the areas of different trapezoids, okay? We're using that XY axis to create trapezoids. So we have 90-degree angles. We drop perpendiculars back to either the y-axis or the x-axis. And the difference in a trapezoid is 1/2 base 1 plus base 2 times the height. So following that methodology out, really what we're doing is we're just breaking the project down into manageable trapezoids where we can take the area, something that we know. You can do triangles. So this is what we ended up coming up with, was almost 7 acres for the area that we had. Okay. Any questions on this one?
So there's a diagram in the book that explains this, right?
Yes. So let me
Okay.
switch over to that and show you guys. All right, where was it? Chapter 12, right? Traversing. See if we get there without breaking my computer. All right, so latitudes, departures, double meridian distance, and here rectangular coordinates. And then areas computed by coordinates. So this diagram really does make a lot of sense once you start thinking about it and looking at it. We're just taking the areas and breaking them into more manageable pieces. So if we take the whole area and go out to the furthest extremes and then back off the other areas, then we find out how that formula plays out. Okay.
And yeah, that does make a lot of sense. I can see from the picture, and it's okay. Yeah, I see.
Mm-hmm. Yeah, that does make a lot more sense. I was going to go through, spell all this out, do the whole proof, and the dazzle you with that at the end, but really, this is one time. Let's just take the formula and go. Okay. The book definitely does a better job of explaining the coordinate method. The other method, the DMD method, it's a little more confusing, and it does say, I didn't catch it on the coordinate method, but you have to have the latitudes adjusted in order to come up with the correct double meridian distance. Okay. If I get some free time, maybe I'll work that out and go through it. All right. So finding the latitude and departure. And this is our measurements off of a north-south meridian, or north meridian. So I think everybody understood that pretty well, how we come up with those, how we come up with the latitude and departures. Very similar to the coordinates. Pretty much had to do that when we were looking at the coordinates anyway, right? In order to calculate the delta y and the delta x. So just like with the leveling, we want to take the difference between our positive norths and our negative souths, right? We want to look at those differences. And how do we end up? Take the difference between our north latitudes, our south latitudes, take the difference between our east departures and our negative west departures. Do we come up with the same number? So as we find out in the next slide, we don't. We are off. But that tells us really a lot about where we're off, how we're off, and what we need to do to fix that. So it's one thing when we're talking about kind of a more simplistic version. To me, the leveling is a little more simplified because for each point, you make one adjustment to the elevation, right? Here, we've got to look at whether we're adjusting a latitude that could be positive or negative, and a departure, which could be positive or negative as well. So those are the things that we've got to watch out for a lot on this. We've got to be really careful. This will trip you up at some point. Take your time, go through this carefully, make sure you can wrap your head around it. Because I keep doing this a lot because that's what my brain does with it. until you slow down and actually just walk through it. So what we end up finding on this one is that our latitude, we have too much north for our south. So we're too far north. And that's what we get by having this positive number here. Our departures, we've got more west than we have east. So we have too much west. Too much west. We have to back it off and bring everything back east a little bit. Okay. So that tells us a lot about how we need to approach these corrections. The formula for the corrections is basically the same thing that we've been doing for all of these other corrections. It's the total magnitude of the error divided by the total measurement times the measurement we're adjusting. So in this case, the length of any one segment divided by the total error value, which is then divided by the total length, which is going to be our perimeter of our traverse. So that's the formula we use to come up with what these values are for the corrections. This is where we've got to be careful and watch for what the sign of that value is. So if we are too far north, we need to reduce our numbers to shift us back down south. And if we're too far west, we need to add to our numbers to bring us back to the east. But you've got to watch out. Am I adding a negative, subtracting a positive? I know that seems like it's one and the same, but you've got to watch out for which direction it's actually going to go to get you back to square. Okay. So we'll take a look at that when I grade the homework. I'll keep an eye on that. But hopefully, does anybody have any concerns about how we go about that? Okay. So our latitude, we're too far north, so we have to come south. So we're going to subtract our correction amount to get our new latitude. If we look at our south latitude, still is too far north, but we need to make it more negative, more south. So we're going to add that value, the correction to that coordinate, to that point. Okay. East and west go the same way. We are too far west, so we need to shift everything more to the east. So we add our correction at this point. Here we've got a western departure. We've got a western departure, so we need to move it further east. So we have to subtract out from that value. And so we subtract our correction value. Does this help? Am I boring the snot out of you guys?
No, this definitely helps because I didn't make the table. I just did it in terms of negative and positive, and didn't actually do it in terms of northeast, southwest. So yeah, it's just a reminder to be more mindful because sometimes I tend to get into a rut, and so this will definitely help me to pay attention and have a little fun with it.
And that's the thing. It's I have a hard time saying always and never, because you've really got to think it through, because you can't just say, oh, to adjust your latitude, you add your correction to your latitude. No. You have to figure out where you are in those quadrants to get you back to that right point in space. Okay. All right. Well, I'm glad this was time well spent. Let's see, was there anything else that we've got? Any other problems you want to review? Anything that stands out? Okay. I've said this half a dozen times. I got my ass chewed over this past week. If you guys have any questions at all about the homework that's coming up, the homework that is due 7 days from now, and you want to join in office hours, or if you can't make office hours and you want to meet separately to go over the homework, absolutely, just speak up, okay? Myself, Marcine is here, Kyle is here. We've all got office hours. They're spaced out throughout the week. They're spaced out in time during the day. You got to be able to catch one of us. The STEM Center, 10 a.m. to 7 p.m., Monday through Friday, plus times on Saturday. Please don't hesitate to ask for help. We can't help you if we don't know you're struggling, if we don't know what you're struggling with. The last thing any of us want you to do is to struggle. So please come to us. We're here to help. I'm getting impassioned by it. All right. Intro to Engineers Scale. You guys get a video. So let's hope that the audio works and hope that something doesn't pop up on the side of what we're going to take a look at. Where's my enlarge?
Oh, sorry. Didn't see it. I was just working on my swell, not to be confused with a grading swell. Today, you will learn about scaling 101 with Thomas Freed, which is me. So a scale is an interesting thing. It has multiple sides, each of which contain different scales. This side 60-30, this side 20-40, and this side 10-50. The interesting thing about a scale is 1 inch equals whatever your scale is. So for example, on the 10 scale, 1 inch would represent 10. If we follow that around 30 scale, 1 inch represents 30. And on the 20, 1 inch represents 20. So you can always use that to measure stuff. For example, let's say we have a line that's exactly 1 inch long, and we're going to claim that that line is 10 miles long. Well, if we were to go to our 10 scale and we measured out 1 inch, we would see that that line, 1 representing 10, is 10 miles long. So let's come to a plan set. Follow me. Here's a plan set, and we're just going to go to the storm page. Now, here at Jacobs, our storm sheets are usually drawn at 40 scale. So here's a bar scale. This bar scale is at 40 scale, and we can tell because the 40 is in the middle. This is exactly 1 inch away from the 0, the 80, 2 inches. So if we align our scale on the 40 side up with this, you'll see that exactly 1 inch away, we're at 40. The 4 is 40. So, all right, let's actually measure something. On this plan set, or on the sheet, we're calling out a 25 linear foot long lateral. So if we put our scale up to it, it should line up at the 25. Which if you see right there is 25. So this plan set was called out correctly. And I know it was because I did it. Anyways, that concludes scaling with Thomas Freed. Thanks, and dig 'em.
You're welcome.
Yeah, thank you. And also, if anyone's interested, I still have my engineering scale and architectural scale as well. So during the lab, if you want, I could bring that, and then we could, I know we'll be focusing on the lab, but maybe have a short sesh or something with it.
Okay. So a little bit more on the scales. So civil engineer scale, mostly. 6 sides, multiples of 10, 20, 30, 40, 50, 60. I will promise you that no matter which way you pick this up, it will never be the side that you're looking for, ever. So never and always apply with this one, okay? That's just a fact of engineering. So we can measure things off. When you guys go and if you look at the solutions to the homework, you'll see that I did my scaled diagram in 1 inch equals 200 feet. So I used my 1 to 20 scale, 1 inch equals 20 feet, or 2 feet, or 200 feet, or miles. 1 inch equals that many units. Multiples of 2s, 3s, 4s, 5s, 6s, okay? We don't have 7s. If you need 80 scale, multiply your 40 times 2. All right, pretty handy dandy stuff. So they come in big industrial desktop sizes. They come in itty bitty little promotional gift sizes. These are phenomenal for surveying. These little 6-inch easy peasy ones fit right in a pocket. They're really great when you're out in the field and you've got it in your surveyor's vest and you bend over and it jabs you in the chin. It's really fun when it does that. These are metal, so they're pretty damn sturdy. You can drop them, you can kick them, you can do anything. This is from North Star Engineering Group, so I'd like to thank them, give a shout out. It's promotional material, so it works. 2 other types of scales. Othello mentioned them. So we have, let me talk about metric real quick because, you know, that just went over so well. So I still have my name on it from when I took the graphics class and had to buy all of these. So I've had this for a long time, let's just say over 20 years. Actually, it's got a bend to it now because it's been in storage for so long. But what this does is this measures off more of a metric size, right? So 1 to 100, 1 to 250, 1 to 500, 1 to 400. So it's more for those kind of units. So 1 centimeter equals 10 meters, etc. Okay. Don't use them a whole hell of a lot. America just did not take on that whole concept. Then there are architectural scales. So whereas and again, I had to roll it because it wasn't the right side that I needed. What you saw in the video was that the scale is 1 to 10. 1 inch on the civil scale is 10 units, and it's divided into tenths. If you look at the architectural scale, it's broken into 16ths. So if you've ever done any kind of carpentry or construction where you've had a bulky tape measure, big tape measure, you might look at it, it could be an engineering tape where it's divided by tenths, or it could be an architect's tape where it's divided by 16ths. So be sure you know what tool you've got to measure. Architect scales are interesting because they're more like the cut add tapes. So you line up on the 0, you go to the nearest whole unit, then back it off to add in whatever your sub measurement is, okay? Quick introduction. We'll have, I think I have some of these. These are engineer scale, aluminum, they're nice. So we'll see if I can get some to hand out when we have our class or have our in-person session. All right, so the architectural scale, similar to tapes. Engineering paper. There's a reason we advocate get the engineering paper. Yes, now that Joanne's gone, I can say I'm okay with graph paper. But the thing about engineering paper, you've seen this green stuff before. It might be hard to see, but on the back side of each page is this much denser grid, right? So you've got little squares and big squares. Your little squares, there's 5 of them to 1 inch. This paper comes with its own scale because of those bold lines in between, separating every 5 units horizontally and vertically, you get 1-inch squares, and then you get the little parts and pieces. So with this, when I say you can sketch it out a lot easier, setting up a coordinate system is really easy. Drawing a 45-degree angle, over 1, up 1, over 1, up 1. You can get your angles pretty close just by a straight edge, right? A 30-degree angle, go over 2, up 1. A 60-degree angle, go over 1, up 2. So those come in handy. So you can get in the ballpark. You don't necessarily have to have a protractor to do the homework, to draw the sketches. I recommend it, but you can still get pretty close just by using engineering paper, and you don't even need a scale. Any straight edge will do. A piece of cardboard could get you through, could get you close. Of course, I'm blanking on who asked earlier. Who was it that does all the homework without doing the sketches? Yeah, you can do it without drawing it. So, and any tools are beneficial. Anything can help, okay? So any questions on everything we've done so far today? All right. Do you guys need a break? Okay. Yes, a break? Okay. 10 minutes, 7:45? All right.
Thank you. I appreciate it.
All right. I was going to say the last one to check in has to sing a song of my choosing, but I'm just not that mean. So, all right.
That'd actually be pretty funny though.
I had a facilitator at a seminar. She said that the last person in had to sing their high school fight song.
Oh no, I can't even remember mine.
Does SoCal High even have one? I have no idea. So anyway, see you guys in 10.